let's get started on the question about malloc implicit free list. Okay, so basically malloc has two interfaces. Basically, there is a function to allocate memory, which returns a pointer. You give a size, and it returns a pointer. And then free, where you give the pointer and expect that to be freed. So let's start with a very simplistic memory management system where you have all this memory, whatever bytes or words or whatever chunks that you want to deal with, they're all free. And every time, let's say you have this sequence. Let's say you get a pointer 1 equal to malloc some 4 bytes. So you will start here, these 4 bytes are allocated. Then, so you track the free space. So this is basically pointing to the free space, and this is allocated space. Then what happens? Let's say you have next malloc call, which asks for 5. Then you will again, you want to allocate 5 bytes or 5 chunks, this and so on. So basically here you are tracking the free pointer in a very simplistic way. Nothing, when you call a free with that whatever pointer, let's say P2, you have lost actually the ability to free this because your pointer has moved forward. So this works when you have almost infinite memory, right? It is not bothered about actually freeing, it's just doing a malloc. Now that's obviously not the real thing. So you need to have a mechanism for tracking not only the free memory, but also track allocated memory so that you can free it. So you need something in the data structure to track both of them. Let's say how you would do. So basically when you do so how do you know, how do you free and a block size, and so that it becomes reusable? That is the first thing. And then how do you represent this free list and allocated list and so on? Let's say we do a simple mechanism to track that. Basically you add, so here is the actual chunk of memory, but you can treat some of the memory as some kind of a bookkeeping cells. And then this is payload cells followed by payload cells. Similarly, bookkeeping cells and followed by payload cells, so on. So what do you keep in the bookkeeping cell? In a simplest form, let's say you have a bit or 1 bit flag. Initially, you have a 0. 0 means free, and 1 means allocated. So you would say 0. Initially, you are keeping track of this, and then let's say you do a P1 equal to malloc of 4. This becomes 4. Okay, and then the payload. This is basically what the application can use, and your pointer. You're not worried about the pointer per se, but your allocator. So next time you do a malloc of 5, you will write, sorry, not 4. I'm jumping a bit. So this becomes 1. And next time you scan this list to find the first overhead block with flag 0, which means it's free. And then you actually change it to 1 and then give it to the application, 5 cells and so on. Here again, you're not able to free it. So, but you're just adding a not 1, but for each block allocated, it's a free or allocated flag, 0 being free and 1 being allocated. So when you move further, you can improvise on that like this. So you again have all the memory free. You can also add, say, the size of the allocated block as well as whether it is free or not. So initially, let's say you have 100 blocks. So your overhead block or bookkeeping block will say 100 0. That means all 100 bytes are available for allocation. And then when you do an allocation with P1 equal to malloc of 4, what happens? This 100, okay, 100 includes, remember 100 includes all the cells, including the bookkeeping cells. So what you do is, when you allocate, you ask for 4 bytes. This becomes 5, not 4 bytes, but 4 elements, and then say 1. So these are allocated to the app. 4 bytes are allocated and 1 for the bookkeeping. So you have already from 100, you're reduced by 5. So you will have 95 and 0 stored here. So you have 95 free this one, right? So now what have you actually, again, you do P2 equal to malloc 5, then 95 will become 89. Sorry, not 90. It will become 6. I will scratch this. I will say 6, and you allocated 6 bytes, 5 for the application, 1 for the reader, and then those are the 5 bytes or 5 cells. Then your remaining free things will become 89 by 0, like that. So you are basically able to start from here. You are able to know how many bytes have been allocated, including the overhead byte. So you are basically creating a list by using the size. So you are able to navigate from these points. Then what happens when you do a free? Let's say you do a free with P2. What happens? The P2 is pointing to the first byte or first cell, first byte that the application uses. So you need to free, that means you need to update this overhead. You have to basically make this 0, and you have to count the 0, how many free bytes are there. So it will become like this. So initially 5 bytes are allocated, 4 are allocated to app, and then you have freed this. So this becomes 6 followed by 0. So initially it was allocated, it becomes 50 bytes plus overhead, and then you still remain this. These are all free 89 bytes that were not allocated at all. So basically, what have you achieved? Your ability to free, and you have updated this. So what happens the next time you do a malloc? You can actually look for, so malloc, you ask for, let's say, 3 bytes. You can start from here, you traverse here, you know that there are 6 available bytes here, you want 3, so you update this to 4,1. So you allocate the 3 bytes, and then you basically say, I have 2 more cells available, so, and they are free. So this is basically what you would do when you do an allocation. So this is basically what is called implicit linked list or free list, implicit free list. Implicit because it is tracked through the size of the allocated chunk and the flag which is allocated or which is free. So the free list is ones with 0, and then you keep traversing to find the nearest or the earliest free chunk which can satisfy the request. Obviously, this is not going to keep track of fragmentation and so on. So what are the things that, so implicit free list is unlike linked list, it is using size as an offset to traverse to find free chunks. Okay. Of course, there are some details which I have skimmed over. So you had this allocated block of 5,1, and then you have a free, which is let's say 6,0 free, 5 bytes are available, and so on. What happens when you do, so let's say it is 6 allocated, of 5 are allocated, and you're asking free, the free pointer is pointing to here, right? So you need to be able to access this header. So it is basically, if the header size is fixed, which is normally the case, the application sees this pointer, your bookkeeping is using a pointer which is actually one chunk, or one cell before that. So that is basically why you are actually not expressing you are not exposing the bookkeeping information to the application. But then this is having a lot of drawbacks, because the application, for example, the one which allocated P1, if this overflows, you have lost all your header information and so on. But basically what you're doing is you're embedding the bookkeeping information as part of the memory that is being managed. But yeah, so basically it has a lot of drawbacks to this. And of course, there are fragmentation possibilities. Now, when you do fragmentation, you have to do a coalescing or defragmentation. Let's look at a scenario where you have allocated something like followed by yeah. So finally, when you're, how do you end this list? You will have a 0 followed by 1. Basically, that means you have allocated 0 bytes. This is the what you call sentinel or terminal cell. Basically, there is no memory available beyond that. When you say you have allocated 0 bytes, it means this is the end of the list. Okay. So let's say you have allocated this. This is P2.
Shouldn't the last one be 1, 1? Because we have allocated 1 byte as the.
Yeah, it's 0 bytes you have allocated. Finally, to terminate this list, it's actually not a normal allocation. You are saying this is the end of this list. So it is 0, 1. So you are basically 1 means you're allocated.
Right. And this is that was the top field. I thought it says it includes both the bookkeeping field as well as the data field, since the bookkeeping field is.
Yeah, you're right. Yeah, that's correct. You're right. Yeah, I overlooked that. Yeah, if that is a convention, yes, you're right. Okay, so in this situation, let's say you do free of P2. So you want to free this memory. Then what happens? This 3 will become 0. Sorry, this 1 will become 0. That is fine. The rest of the things will be remaining. And then let's say this is P3. And I don't know how many are 1, 2, 3. 3 cells have been allocated. So this will become 4, 0, and so on. Let's say you just do another malloc. Let's say P5 equal to malloc of let's say 7. No, not 7. So you have a malloc of 4 bytes. Okay. See, basically what happens, you have free memory, but you are not able to allocate because the size exceeds. So you basically, you have free size here, which can actually be allocated. So here is 4, 0. If you see this, these are free. You could have allocated 5 bytes from here. Okay, sorry, I'm saying 5 here. 5 bytes could have been allocated if you have, basically this is also freed. I'm sorry, free is done P2, P3. but your bookkeeping is keeping track of them separately. You have 040, just you set the flags to free, but you are not counting that these are contiguous, and you could have allocated for 5 bytes from here itself. Instead, you would go further down. So they basically are ending into fragmentation of memory. So the idea is that you are not recognizing contiguity of the memory, free memory, in this data structure that we are using. So you need an operation which can actually coalesce these contiguous memory. So that is called coalescing. I'm not sure about the spelling. Okay, so unless you do that, then what happens when you do that, this will become normal cell. This you will add this, how many other cells are available. So 1, 2, 3, 4, 5 plus 2, 7, 0. So basically the coalescing will update this to 70. So this next malloc 5 could have been allocated from this point onwards. So that's basically the principle of defragmentation or coalescing, bringing the contiguous memory together. Now, when to do that is as a policy. So you could do it periodically or always when you do a free, or when no available chunk. These are all various policies independent of whether it's an implicit linked list or whatever implementation. So you do these 3 options you have for defragmentation or coalescence. Right? Now each has its own pros and cons. Always when freeing, then you always have the best best utilization of memory. Right? So free will always immediately compact the adjacent cells, so you could always allocate without traversing this list too far. You could, yeah.
So for the coalescing, if it's a forward coalescing, then that's easy, right? When you are doing free. But if it's a backward, the one that
good point.
Sequence of event that you have shown, right? That might require explicit traversal from the start.
Doubly linked list, right? In a linked list. Similar thing you could do with the implicit free list also. Yeah, you're right. So if basically what Subhash is saying is that we conveniently assume, so this is allocated, some k bytes are allocated, and then we have a free. So let's say 3 bytes free, and so 3 bytes free, and then another 5 bytes free. Now this became free now, but while doing this, you need to coalesce. You don't have handle to this at this point in time. So you have to traverse. You have to coalesce this way. You're not always coalescing forward. If this is forward coalescing, this is backward, right? You have to do both. So how do you do that? Basically, you need to obviously keep track of the count in this direction also. Just like you can use this as an offset, you should be able to use another count as an offset to traverse in this direction to access this header. So that is basically, it's like 2 pointers. These sizes are nothing but offsets if you treat them as index to an array. And that's basically that's all there is to it. The rest is all similar to a linked list operation here. So you keep track of allocated size or allocated or free size, and then size of basically what you're saying, that basically how far do I need to move to size of the or index of the previous free block, adjacent free block. Yeah, so you're right. you need to go forward, and bidirectional traversal you can. That is called actually in the implicit linked implicit free list terminology. It is called footer, and the forward one is called header. That's the terminology used typically. Okay. So Subhash, are you clear what I was trying to explain?
Yeah. So I mean, so the last point is important. So we could have a size, the backward size as some negative number, or we could have a footer right before the header of my block, right?
Yeah.
To know the size of the previous block. Okay.
Yeah. Yeah, but these are all, I would say, I haven't seen implementations which actually do this, because the biggest fear is that application can wipe out any of the bookkeeping information you have. It's better to keep that information separate. And there is a lot of locking that one needs to do because of the pointer manipulation or whatever manipulation. And you might not be wanting to do that in the memory that is allocated to application. So it's normally a typical practice to keep bookkeeping data separate from application memory. Even though the bookkeeping information itself can be still implicit list or otherwise, that is different. Okay, there are two questions. Senthil, yeah, okay, I'll unmute you, Senthil. Okay, you're saying something, Subhash.
No, I was just saying, like, so your last point, I just wanted to clarification on. So what we are saying is all of this bookkeeping data is part of the memory now, and there's always chance to overrun by application, right? So I mean, the allocator who asks for the memory, and it tries to overrun the buffer and can wipe out the metadata. So this is not the suggested option, or like libraries don't implement like this, or?
As far as I know, they don't implement like this, but I haven't looked at all possible implementations actually.
Okay.
So the thing is, it's a common sense thing that you're giving control to the application, and applications could actually go haywire intentionally or otherwise. So you lose complete control over the heap. So heap memory can be separate from the bookkeeping information. So that is the logical thing to do.
Okay.
Okay, so that's about malloc. Now Senthil's question about design criteria for bare metal versus RTOS.
Hey Raghu.
Sorry.
Yeah, who is talking?
Sorry, go ahead. I think there are two of us.
Hey Raghu, yeah, this is Bhargavi. I had a question about the malloc that we just spoke about. So, so for having this forward and backward type of coalescing, so typically the structure is like a doubly linked list structure that gets used. I'm just curious, like, could you maybe highlight some or show some how the structure looks like, or is there like any pseudocode or actual library code implementations that we can go and look at for this?
You can look at GCC's library. Okay.
Okay.
CLib or C++. I don't have it handy, so in the limited time I won't be able to show it. Maybe I can, if I can show it in the next class, or if you want to go through that, you can do that. There are many variants, and I mean, it's a very popular topic, especially when it comes to race-free, lock-free mallocs and so on. But in my limited understanding, it is typically, it doesn't matter whether it's a implicit list or it's a linked list. Compilers can do a good job of efficient access, so it's not a big deal. The thing is, I don't use malloc and free in an embedded system normally, right? C++ has a built-in heap, so because of what you call, when you instantiate an object, you need to allocate memory for it, and then there are virtual functions and so on and so forth. It's a bit complex, so the methods have to be also stored as part of the objects. The function pointers for the methods have to be stored and so on. So whereas in C, in embedded systems, you can always get away without using malloc and free. So application need not call malloc and free, but C++, when you actually do and you declare an object instance, when you do that, it has to allocate memory for all the methods, the pointers to the method functions and so on. So, and private data, etc. So it is more complex in C++. So it's more likely you would see heap being configured during the startup when you use C++. And if you are using pure C, you don't even need a heap.
Okay. Yeah, if you do come across some implementations, if you can share it, the link at least, that would be great. I'll also keep it.
I think the C programming book by KNR, Dennis Ritchie and Cunning, though that has at least this kind of implementation code as well, if I remember correctly, but I have to recheck.
Yes, it does, but a lot of things have changed since then, so it may be quite outdated.
Yeah. No, Bhargavi's question was very specific to this implementation of implicit free list. So I think you also mentioned, right, that this may not be a best approach in general because of other issues like metadata getting overwritten and so on. But if for an interview point of view, if someone wants to implement, with this approach, I think there is some implementation there.
Yeah, thanks, Subhash.
Yeah, I'll check it out. Thanks.
Anyone else?
Yeah, Raghu.
Please raise your hand.
Yeah, Raghu, I had a question on this. So you mentioned about one of the obvious drawbacks of this approach, where the application, could override the metadata information, right? So, so the point of then discussing is this basically from an interview perspective, this could be suggested as a solution for malloc and free, and then state the disadvantages that you told. Is that why you discussed?
Yes. Yes.
Okay.
Yeah. So it's not really in the real world, but do you understand the principles of heap memory management and the simplest management? So basically, why do you need to keep track of free list? Why do you need to keep track of the previously freed memory and look at contiguity and coalescing, concept of fragmentation? All these principles are easily illustrated in this implementation. That's the idea. Okay. Yeah, you need to be also aware of the limitations and potential hazards.
Makes sense. Thanks.